All right, today's content I'm really excited about. Is that a good thing or a bad thing? I think it's super interesting. We're going to focus a lot on relating the theory and the simulation ideas in some, I think, pretty neat ways. And stay tuned for next Tuesday, when I'm going to emphasize something that I did a few years ago when Dr. Wetzel was still around. I made a simulation of the game Chutes and Ladders. I made a simulation of Chutes and Ladders on Mathematica. So I'm going to show you that on Tuesday as kind of a fun thing to do with simulation. That, well, the point is that simulation is sometimes absolutely necessary. Sometimes you can't really figure out formulas for various situations where probability is involved. For example, like Chutes and Ladders, where you've got the spinner that spins 1 through 6 with equal probability. But the thing that makes it difficult is you got all the chutes and ladders, right? You got all the ladders going up and all the chutes going down. And they're kind of in random spots. So how do you model such a thing? Theoretically, that's kind of a difficult thing to model. You might be interested, for example, in on average, how many spins does it take you to reach the top? That would be a difficult thing to model as an abstract random variable with formulas. But I did get Mathematica to simulate it. And we'll see what the answer is on Tuesday, next Tuesday. Another important reason that simulation is necessary is it helps confirm theoretical calculations. And that's what we're going to emphasize today. Okay. So let's start with a little theory related to chapter 4. Mostly we'll focus on chapters 4 and 5 today, though every once in a while I'll talk about something from chapter 6 as well. Okay. So let's start by considering an example. I could call this an exercise. So we're going to think about the theory through the context of examples. These are pretty enlightening examples, I hope. Okay. Suppose you've got two random variables that are both uniformly distributed on the interval from 0 to 1. Well, let's go ahead and call them, say, U1 and U2. They have the same distribution, uniform 0 to 1. That would mean their PDF, these are continuous. So we're talking about a probability density function. Their PDF has a graph that, well, technically speaking, is 0 when x is negative. Then it jumps to 1 when x is between 0 and 1. And again, it doesn't matter where you put the open circle. I think it's actually most traditional to put the closed circle there and the open circle there. In other words, to say the value equals 1 when x is strictly between 0 and 1, but it doesn't matter, right? Because it's continuous. So there's the PDF. And the CDF is the integral of the PDF. And it's going to look like this. That make sense? You integrate the PDF to find probabilities. You find differences in values of the CDF to find probabilities. The CDF is the integral of the PDF. When you integrate the PDF, certainly when x is negative, you get negative values for the CDF. Then when x is between 0 and 1, you're essentially integrating 1, meaning you get x. That's the graph of y equals x there. Plus c, but the c is going to be 0, so that the graph goes through the origin there. And then when x is bigger than 1, the integral of the PDF from negative infinity up to some value bigger than 1 is just the area under that part right there, which is 1. CDF stays at 1. So both of these random variables have the same distribution. They have the same PDF, the same CDF, the same mean, the same variance, same standard deviation. They have all the same properties. However, when I'm considering more than one random variable at a time, they could be, I could design the model, so to speak, for them to be related to each other, dependent, or I could design the model so that they're unrelated, independent. For example, one way to design the model, you might say, to make these dependent, I'm not going to do this, but I could, is I could say, for example, U2 equals 1 minus U1. Then they'd be dependent, right? They'd be completely related. They'd be completely correlated, in fact. If I said U2 was 1 minus U1, they both would still have this distribution. Because if you take a random number between 0 and 1 with a uniform probability on any tiny interval of the same size, and you take 1 minus that, that is also, I hope intuitively, going to model a random variable that's uniform on 0, 1 as well. You know, if your random number that's generated is 0.8, 1 minus 0.8 is 0.2. If it's 0.25, 1 minus 0.25 is 0.75. So that would be an example of a way to relate these. They would not be independent then. But it's usually best, easiest, you might say, most useful, to assume they're independent. Assume U1 and U2 are independent. Now that's going to imply stuff related to chapter 5. It's going to imply their joint PDF, joint probability distribution, as a multivariable calculus function, is a product of their individual PDFs. Fairly simple here still, although the joint PDF would be defined on a plane, a U1, U2 plane. Its values would always still be 1. I will consider that later in the class today, but for the moment, I'm going to do something different. But we're still going to need the assumption of independence. It's an assumption. To do the math, you make the assumption. To apply it in real life, you ask, is the assumption reasonable? That's how you apply it in real life, is you can't really prove independence. You just need to say it doesn't seem reasonable. And you hope it's, I mean, both logically reasonable and maybe based on data, it seems reasonable. I'm going to do something different. I'm going to consider new single random variables, not multivariable. Call this example 1. Well, okay, let's call this sub-example 1. I'm going to have, this is going to be my main example. It's going to have 3 sub-examples. Sub-examples meaning in the same situation. You've never heard of the word sub-example, have you? I haven't either. I just made it up. Makes sense. Let's let a new random variable, let's call it capital V, equal what? How about the bigger of U1 and U2, maximum of U1 and U2? I might wonder, what's the distribution of V? And when I say distribution, I'm including both saying find the PDF, find the CDF, maybe find the mean, find the variance, find, you know, numerical summaries, parameters that describe the distribution of this new random variable. What's going on here? As an equation relating random variables, it's a purely abstract thing. How would you apply this idea in real life if you are observing values of U1 and U2 that are uniformly distributed between 0 and 1? Maybe U1 ends up on the first observation, U1 is 0.7 and U2 is 0.85. The bigger of those is 0.85, so the observed value of V is 0.85. You do another observation of the 2 random variables, maybe U1 is 0.94 and U2 is 0.36. The bigger of those is 0.94, so the observed value of V is 0.94. Always take the bigger one. Now, uniform distribution on 0, 1 obviously has mean at 1/2. Center of mass. I hope it makes some intuitive sense that if you're always taking the bigger one, probably the mean is going to be bigger than 1/2 for the maximum, right? Both U1 and U2 have an equal probability of being less than 1/2 or greater than 1/2. But on a random observation, most likely, or more likely than not, you might say, one of them is probably going to be bigger than 1/2, and one's probably going to be less than 1/2. I mean, they could both be bigger than 1/2 and both be less than 1/2. That could happen. But on average, more than 50% of the time, probably one of them is going to be bigger than 1/2, and so therefore the maximum is going to be bigger than 1/2. Probably the mean of this distribution is bigger than 1/2. Let's see if we can verify that theoretically, and then we'll try to confirm it with simulation. So here's that second application of simulation, confirming theory. First application, perhaps more important, is doing things when the theory is too hard. Second application, still important, is confirming theory. When you're unsure about the theory, perhaps, do a simulation and see if it confirms the theory. Let's do the theory. How do you find the distribution of V? Same technique as Tuesday. Find the CDF first, and then differentiate it to find the PDF. That was the technique of Tuesday. The CDF of V, capital F sub V. I guess I should call its variable little v, maybe, cursive V. So that's a cursive V. You could, it sort of looks like the Greek letter nu as well, NU, which we hardly ever use, but remember, by definition, the CDF is always, right? A probability that the random variable, the capital letter, is less than or equal to the given little quantity, which is a real number, ordinary variable. It's always the case whether your random variable is discrete, continuous, or mixed. We haven't done a mixed example yet, and I don't think we're going to get to it today. Perhaps next Tuesday again. That's always what the CDF is. Again, the way you compute it depends on whether your variable is discrete, continuous, or mixed. But in theory, this is always what it is. Now, our variables are continuous, so in theory, I could compute this perhaps with maybe an integral or something, but let's not worry about integrals for the moment. What would be a good goal here, perhaps? Well, use that equation somehow. And the only obvious way to use it at first is just to plug it in there for V. So do that. Keep the little v as it is. I'm plugging in for the capital V. Then you stare at this for a while. And you stare at it for longer. Then you go get some coffee. Or today I actually brought water. Go get some coffee, stare at it for a while. I don't know what to do. What do you do with this? Well, okay, that's an experience many people experience, including me sometimes. Ask yourself, what would it mean if the bigger of two quantities was less than or equal to some other quantity? What could you say about both quantities? If U1 and U2 are, their maximum is less than or equal to V, what could you say about both U1 and U2? If the bigger is less than V, they're both less than V. I could rewrite this fact as saying U1 is less than or equal to V, and I'll go ahead and put the word and in there. Maybe I should put intersect. U2 is less than or equal to V. It gets a little funny if you put the intersection symbol because it's like, well, what are the sets? What are the events? Well, they're continuous events. It gets a little confusing if you put the intersection symbol. It's okay if you do. This is a little bit more intuitive, just put the word and. Okay, I guess that's progress. Any bright ideas for more progress? And, where have we seen and or intersections before? Chapter 1, 2, 3, 4. Two, right? Chapter 2. Multiplication rule. Hey, and I'm assuming independence. Assume just what you need to avoid conditional probabilities. I can say this is the product of the probability that U1 is less than or equal to V times the probability that U2 is less than or equal to V. This feels like a lot of progress, doesn't it? I guess. And I know the distributions of U1 and U2, they're both uniform. You know, the CDF looks like that. These are CDFs. And here's, I used the independence. That should be pointed out, independence. Well, I mean, these things are piecewise functions. Is that going to mess things up? Well, you know, the domain of most interest is when the input is between 0 and 1. If U1 and U2 are, you know, they take on values between 0 and 1 with non-zero probability, so will their maximum. I really need to only assume when I do this calculation that little v is between 0 and 1. And then I can use the formula for the CDF. What's the formula for the CDF here? I haven't used the letter X, but maybe I should call it capital F of X is X when X is between 0 and 1. I mean, maybe I should have called it capital F of U is U. But, you know, the variable name doesn't matter. It's the idea that matters, the formula, the recipe. That's the function I'm plugging the V into there and there. Oh, hey, it's pretty simple. V times V, V squared. Isn't this nice? That's pretty nice. And that's the CDF. What about the PDF? PDF of V. Once again, assume V is between 0 and 1. It is sort of nicest to not worry about being at the endpoints, because then you don't have to worry about the differentiability issues. Little f sub V of V is the derivative of capital F sub V of little v, which is going to be 2V. Are these valid CDFs and PDFs? Yeah. The PDF has a graph that looks like this. And yes, it's 0 elsewhere. That's the number 1 there. And it's the area under the PDF is a triangle, area of a triangle, 1/2 base times height. Base is 1, height is 2, the area is 1. Well, and we already knew that from the graph of the CDF, the graph of V squared, when V is between 0 and 1, looks like that and goes up to 1. And yes, technically it's 0 when V is less than 0, and it's 1 when V is bigger than 1. And now you can see visually this PDF as a density function has a center of mass that's going to be bigger than 0.5, right? The graph is higher when the input is bigger than 1/2. Data, simulated data, is going to be more dense close to 1 than it is close to 0. you're going to get a mean bigger than a half, just like we expected. What would the mean be? What's the expected value of V? Mu sub V, if you like. Got to integrate V times the PDF over the domain where it's positive. Integral from 0 to 1 of V times little f sub V of V dV. Trying to make my V's cursive to distinguish them from uppercase. My little V's. So that's integrating 2 times little v squared dV. Because there's the PDF. And that's going to give 2/3 little v cubed evaluated from 0 to 1, and that's going to be 2/3. How about that? Yeah, bigger than 1. 0.6 repeated. How about the variance? Well, find the second moment first. We could also do this by finding moment generating function and differentiating it and plugging in 0. And you should be able to do that too, by the way. Should be able to find the moment generating function here, although to do the integral for the moment generating function, you'd have to use integration by parts. I'm not going to go through the details, at least not right now. Here's the second moment. You're ultimately going to integrate 2v cubed from 0 to 1. That'll be 1/2 v to the 4th from 0 to 1, and that means the second moment is 1/2. And therefore, the variance, some people were forgetting that the variance is not the second moment. So it's an easy mistake to make, but it's always the second moment minus the square of the first moment. Get a common denominator of 18. And 9 minus 8 over 18. Looks like the variance is 1/18, but did not make a mistake. I think that's good. Could also label that as sigma squared, sigma sub v squared. And then the standard deviation, sigma sub v, is the square root of the variance. That'll be square root of 1/18, which will be 1 over square root of 18. And I don't care if you leave the square root in the denominator, it's okay with me. I mean, you also could write this as square root of 9 times square root of 2, which would be 3 square root of 2. You can leave it like that. You can rationalize the denominator if you want. You don't have to. Multiply the top and bottom by square root of 2, and you write it this way. All those are okay, exact forms of the answer for the standard deviation. And it's bigger than the variance, right? Because the variance is less than 1. Take its square root. It's about 0.2357 for the standard deviation. There you go. Yeah, any of these is okay. By the way, if you're going to be planning to be a teacher, and you always remember your 7th grade math teacher saying, rationalize the denominator. We don't want any radicals in denominators. It's against the law. No, it's not against the law. It's okay. Dividing by 0 is against the law. But you can have roots in denominators. It's okay. So why do they teach you rationalize the denominator? Because it's a useful skill to know sometimes. It's helpful to be able to do to simplify things sometimes. So there we go. Can I clarify anything there? You know, with normal distributions, we have the 68, 95, 99.7 rule. That, for example, says about 95% of the data, if you're talking data, or about 95% of the probability, if you're talking probability, is within 2 standard deviations of the mean. Does that rule work approximately even when your distribution is not normal? Very hand-wavingly so. a very vague rule of thumb is, yeah, most of the data or most of the probability is within 2 standard deviations of the mean. The mean is 0.6 repeating, about 0.67. 2 times the standard deviation is close to, what would it be, 0.47. 0.67 plus or minus 0.47. Well, plus 0.47 brings you past 1. 0.67 minus 0.47 is 0.2. So yeah, most of the data, most of the probability is between 0.2 and 1 effectively. And you can see that it's not a very precise thing to say, but certainly can be said. Chebyshev's theorem, Chebyshev's inequality can also be brought to play to get a lower bound of the probability, but let's not worry about that. I said I wanted to relate this to simulations, so let's do so now. And you'll once again be doing something similar to this in your homework for next time. So again, equals rand generates random numbers between 0 and 1 with a uniform distribution. Of course, every time you copy and paste, it changes. I do want to do a bigger sample here. That's going to cause me to have to make this small enough that you won't be able to see it real well. I think I'd like to do a sample size 100. Oops. My mouse pad or trackpad is kind of goofy. It's always doing things I don't want it to do. So let's go down to line 100 here. So there's 100 observed values of a uniform 0-1 distribution. I could copy and paste this entire column over, which I guess, yeah, okay. And you get another 100 observed values. Of course, again, every time you copy and paste, everything changes, which is why it's then nice to actually also do a copy and paste special. So I'm going to copy, Control C, and over here I'll paste special, values only. So then we have it now fixed. And so if I copy and paste anything over here again, all that stuff changes, but these things are staying fixed. Just kind of nice to have something that's staying fixed. And yeah, I could take the maximum equals max. Like that. It'll take the bigger. And those are fixed numbers, so it's going to stay that way. So 0.39656 is the first bigger one. For the next one, we should get 0.793399. Yep. Ignore these 2 columns now and focus on these columns. Maybe I should have put a space in here. Insert column to the right. Next one's going to be the 0.84, 804, etc. I'm always taking the bigger number. I do equals average here. Should be close to 0.5. It is. Next one's close to 0.5. But the last column, it should be close to 2/3. 0.67. Yeah. Cool. Confirming the theory. Yay, that's what we were after. Doesn't that feel nice? How about the standard deviation? That was about 0.2357. For a uniform distribution based on the exercise you did, it's actually not one of the ones I graded. For where was it? Well, okay, let's just look at the table. uniform distribution, constant PDF on a finite interval, 0 elsewhere. Its mean is the midpoint, makes intuitive sense. Its variance is the length of the interval squared divided by 12. So its standard deviation is the length of the interval divided by square root of 12. Talking about the uniform one here, not V. 1 over square root of 12. Oops, sorry. 1 over square root of 12. About 0.2887. So if I do standard deviation here for these, should be close to 0.29, say. 0.27, 28, 0.29, somewhere in there. Yep. But with V, it was closer, it should be smaller, closer to 0.24. Yep. And you could also make histograms of these things, which, histograms are essentially data-based ways of visualizing the PDF. So I could insert a chart and pick the histogram option for me. It doesn't always do that. So that's a histogram of the first column, which was from uniform distribution. Of course, it's not going to be perfectly horizontal because it's simulation. But there's no clear up or down pattern to this. It's not an increasing function clearly or decreasing. But for the other one, it should be pretty clearly increasing. So the last column. Insert chart, histogram. There we go. Yeah, pretty clearly increasing. Well, that's because the PDF looks like that. Sub-example number 2. How about instead of the maximum, we take the minimum? Sub-example 2. Let's say W be the minimum of U1 and U2. By symmetry, we should be able to predict the answer. But for the PDF, instead of a line through the origin with a slope of 2, having min value at 0 and max value at 2, probably it's a line with a slope of -2, having a value of 0 at 1. Wouldn't that make sense by symmetry? For the graph of the new PDF here, for the new example, sub-example to look like this. I'm not going to draw it there, but by symmetry. Let's see if that happens. CDF of W. Capital F sub W of little w. By definition, the probability that capital W is less than or equal to little w, which is the probability that the minimum of U1 and U2 is less than or equal to little w. Once again, we're going to assume the variable, in this case, little w is between 0 and 1. Now you got the smaller of two given quantities being less than or equal to the smaller of U1 and U2 being less than or equal to a given quantity. That means one or the other is less than or equal to that. Or instead of and. Right? Could be both less than W, but at least one. One or the other. Or is always an inclusive or unless you say otherwise. So that's equivalent to a union. Does that mean I need the addition rule? We could try it that way, I think. Yeah, okay, that's one way to do it. I was thinking of a different way initially, but that's one way to do it. Do the addition rule. You want say U1 is less than or equal to little w, or U2 is less than or equal to little w. The general addition rule would say that's the probability that U is less than or equal to little w plus the probability that U2 is less than or equal to little w. That's a W there. Minus the probability that U1 and U2 is less than or equal to little w, which by independence is going to be the product. So there I'm using the multiplication rule as well. That's by independence. In particular, the independence is used on this part right there. Initially, it's really the probability that U1 and U2 are both less than or equal to W. Intersection for and. The multiplication rule for independent events, since I'm assuming independence again, would allow me to replace that. Once again, the PDF or the CDF of a uniform looks like that. And between 0 and 1, its output equals its input. Therefore, this should be W plus W minus W squared. 2W minus W squared. Also the same as W and times in parentheses 2 minus W. When W is between 0 and 1. Not elsewhere. The PDF then is the derivative of that. PDF of W little f sub W of little w is the derivative of the CDF. Differentiated in that form, you're going to get 2 minus 2W. What do the graphs of these things look like? Graph of 2 minus 2W. It's a line with a slope of -2 and a vertical intercept of +2. There it is, just like I predicted. And the CDF is the integral of that. And do notice, this is the formula that's valid between 0 and 1. And it's as you let W approach 0 from the right, it does approach 0. The value of this expression is 0 when W is 0. And as W approaches 1 from the left, the value of this expression approaches 1 times 2 minus 1, which is 1. It's a parabola, piece of a parabola, opening downward because the coefficient of W squared is negative. In fact, the maximum value of the parabola is going to occur when its derivative is 0, which is at 1. It's going to be just like this, half of a parabola. And if I continue the parabola, it would have a maximum value at 1, but don't continue it. This is what the graph of a CDF looks like. You would think by symmetry, instead of the mean being 2/3, it should be 1/3. Variance, though, probably is the same. Same amount of spread. Although if the mean changed from 2/3 to 1/3, I guess the second moment must change. Let's see what happens. Mean of W, the expected value of W, by definition is the integral of of little w times the PDF of W as W goes from 0 to 1. There's the PDF. That's what I got to integrate times W. 2W minus 2W squared. That's going to be 2/3 W squared minus, excuse me, W squared minus 2/3 W cubed. Evaluated from 0 to 1 is 1 minus 2/3 is 1/3, just like predicted. Second moment. You're going to end up integrating 2W squared minus 2W cubed, right? Because it'll be the same formula as this one, except with a W squared in there. So that'll be 2/3 W cubed minus 1/2 W to the 4th, right? Check my work there. 2/3 minus 1/2. 4 minus 3/6 is 1/6. Yeah, it had to be different. The second moment for the other one was 1/2. It had to be different since the first moment was different. If we're going to get the same variance, the variance in the end should still be 1/18. Variance of W. Second moment minus first moment squared is hopefully still 1/18. 3 minus 2/18, yep, 1/18. And then the same standard deviation as before. Makes good sense that should be the case. Same amount of spread by symmetry in the PDF. On the spreadsheet, let's confirm that. Take the minimum. Can't see that. I just type equals min of D1 comma E1. Its average should be close to 0.33. It's not going to be 1 minus 0.6775 though, in all likelihood. Because that's data, and these things are independent of each other. And yes, it's not 1 minus that number, but it is close to 0.33. And the standard deviation should be still close to 0.24. But again, not exactly the same as the other one, even though the values are frozen. If I made a histogram, it would be a decreasing histogram. PDF looks like that. I think that's pretty cool. Can I clarify anything? Let's do sub-example 3 now. And we'll have a sub-example 4 as well. Sub-example 3. Actually, I'm going to just focus on one of the U's, not both of them for this one. Let y equal U1 squared. On Tuesday, we looked at the square of a standard normal random variable, and we saw it had a chi-square distribution with 1 degree of freedom. Now we're squaring a standard uniform distribution, uniform random variable. It's uniformly distributed over the unit interval from 0 to 1. Look at the CDF. Capital F sub y of little y, by definition, is the probability that capital Y is less than or equal to little y. Now go ahead and replace capital Y with U1, squared. I hope it's becoming familiar enough by now that you realize you should take the square root of both sides of this inequality. And unlike the normal distribution, where we had to think about plus or minus square root because of the symmetry of the normal distribution about 0, this particular random variable, y, well, u1 to begin with, only takes on positive values between 0 and 1. So I really need to only simplify it like this. It's different than the standard normal example. And I don't have to think about negative values. I mean, I could say this has got to be 0 is less than or equal to u1 as well, but we already know that happens, so I don't have to bother writing it. That as a side comment, this does equal the probability that this is true as well. Those are equal because of the nature of u1. It's uniform 0, 1. And that's going to be related to the CDF of U1, which, as it's always been in all these sub-examples, it's the same CDF still, where the output equals the input. This will equal the square root of y, whatever's there. I guess that's the CDF, and its graph would look like this, and it does go from 0 to 1 as the input goes from 0 to 1. It's not a parabola. It's steeper near the origin than a parabola is. In fact, it becomes infinitely steeper as you approach the origin. That's the CDF. So the PDF is going to be its derivative. 1/2 y to the negative 1/2. 1 over 2 square root of y. The derivative has a vertical asymptote at 0. Interesting. That's related to the fact that the PDF has a vertical tangent at 0. The derivative is undefined at 0. And when y reaches 1, you're down to 1/2 here. You might wonder, does the integral of the PDF even converge? Because technically speaking, because there's a vertical asymptote, it would be an improper integral. The answer is yes, it does converge. But because it gets so high near 0, if you've got thousands of data points that this is modeling, they must be clustered really densely close to 0 because the graph gets so high. If you got, say, thousands of them. Now, if it was only tens or hundreds, they may not look super clustered close to 0. But if you had thousands of them, they'd be very, very dense near 0 because that PDF gets so high it is unbounded near 0. But the integral of this does converge, and it converges to 1 over this interval from 0 to 1. You can check that on your own. It's an improper integral, so technically it's a limit. Look in your Calc 2 book if you want examples. What's the mean? Since the data is clustered so close to 0, PDFs are really idealized histogram when your data is an infinite set, essentially. Your mean is going to be less than 1/2 for sure. Integrate y times the PDF, and then you actually get a proper integral. If you multiply this times y, you get 1/2 times the square root of y, right? Because the y divided by square root of y is square root of y. It's no longer an improper integral. You might wonder if you need to justify that this is okay. It is. Do the integral. Dividing by 3/2 is the same as multiplying by 2/3. 1/2 times 2/3 is going to be 1/3. Huh, okay. The answer is 1/3. Happen to be the same as the mean of that triangular distribution from sub-example 2. Just a coincidence, I guess. Yeah, it's more dense near 0 than sub-example 2 was, because this doesn't have a vertical asymptote. So you might think because of that, the mean should be smaller than 1/3. However, it's more dense near 1 than this example was. So the density, the higher density near 0 and the higher density near 1 compared to this example somehow evens out to make the mean still 1/3 the same. But I wouldn't have necessarily predicted that ahead of time to be exactly the same. Second moment, you multiply by another y, get y to the 3/2 here. One half times 2/5 is 1/5, and the answer for the second moment is going to be 1/5. And there for the variance is 1/5 minus 1/3 squared. 1/5 minus 1/9, get a common denominator of 45. I guess that'll be 9 minus 5 over 45 is 4/45. And then the standard deviation of y is going to be the square root of that. It'll be 2 over square root of 45. 45 is 9 times 5. You could write this as 2 times square root of 9 is 3 times square root of 5. And if you like rationalizing the denominator, you can write this as 2 square root of 5 over 15. Anyway, there's the variance, take its square root. It's about 0.298. You can confirm it like this as well. Not the same variance as the other example, which I guess you would think that probably would happen. Yeah, the means happen to be the same, but the variance and standard deviations are different. Can we simulate this? May not have many problems from the book due next Tuesday. I'll see if I can find a few. It might be mostly problems that are spreadsheet simulations and theoretical verifications like we're doing for these sub-examples. Problems that I make up, essentially is what I'm trying to say. Could we simulate this? Yeah, you could take d2 and square it. Or e2 and square it, in fact. Because D2 and D1, I meant to say, column D and column E are both random samples from uniform distributions. So I could square either one. They're different simulations, so I get different answers, but they should be similar. There's my mouse trackpad again. It's not as dense near 0 as I was expecting just looking here, but and there's a number real close to 0. That density near 0 is for really numbers that are really close to 0. You have an inordinate numbers that are really close to 0. Means close, yeah, we want it to be close to 0.33 repeating. It is. Standard deviation should be a little bit bigger, closer to 0.3 perhaps. Yep, okay. Of course, when you do simulations, you all get different answers. That's okay. It's supposed to happen. Slightly different. Sub-example 4. Sub-example 4. And this is going to be related to chapter 6. So here's, I'll get a little bit of chapter 6 in here. So maybe I will also assign a problem or two from chapter 6. We'll see what I can find. Let S be the sum of U1 and U2. Add the random variables. In problem sets, we did that. We added random variables before. You might even remember we can find the moment generating functions when they're independent pretty easily. Remember that when you add two independent random variables, you multiply their moment generating functions. Remember that from problem stats, chapter 7. So we can find the moment generating function for U1 and U2 pretty simply. Let me go ahead and find it here. X1 and X2 are independent, and Y is their sum. Then the moment generating function of Y is the product of the moment generating functions for X1 and X2. So we could approach it that way. I think I'm not going to, because actually, if I do, we'll see a moment generating function that will not match the table in chapter 4. So we won't be able to use the fingerprint theorem because of that. Identifies random variables by their NGFs. So let's use a different approach to try to describe the distribution of S. Let's find its CDF. Capital F sub capital S of little s is the probability that capital S, maybe for the capital S, I should do that. I won't bother except right there, but that's the probability that U1 plus U2 is less than or equal to little s. Are we trying the same technique as before? I'd need to isolate U1 on one side, but then I have a U2 on the other side. And if I had tried isolating U2, then I'd have U1. It's not so clear what to do here. And in fact, adding random variables and finding their PDFs in general is a very difficult thing. And the abstract case, at least with the assumption of independence, you end up computing the PDF as something called a convolution. Maybe you've heard of that word, probably you haven't. Physics majors hear of it. We will talk about convolution in here in the discrete case next week sometime, maybe Tuesday. Probably Tuesday, we will. In the discrete case, it's easier to think about convolution. In the continuous case, it's hard. However, we still can figure this out. So what we can do is we can think about the joint density of U1 and U2. The joint density of the bivariate random variable U1 comma U2 as a point or a vector by independence that joint density would be the product of the joint densities of U1 and U2, of the densities of U1 and U2 individually. Now those densities are the same because U1 and U2 are both uniform 0, 1. So they both equal 1 when they are in the domain where they are positive and they're 0 or elsewhere. 1 times 1 is 1. Anything times 0 is 0. This is going to be, as a multivariable calculus function, a piecewise function where its output is 1 if both U1 and U2 are between 0 and 1. I could write that like this. And 0 otherwise. Its graph in three-dimensional space is going to be a horizontal plane above the square where U1 and U2 are both between -1 and 1. There's the graph right there above the U1 U2 plane. The bigger plane is like that, and the square where U1 and U2 are both between 0 and 1 is like this, and the graph has a value of 1 up there. The volume underneath that graph is 1. It's a cube. It is a PDF. That's what I'm trying to say. And this probability can be thought about using this PDF. And effectively, because the height of this graph is 1, the volume, numerically speaking, under the graph is the same as the area above the square, or the area of the square. And that holds for subsquares of the bigger square as well, or subregions of the square. So what I'm trying to say here is, what you want to do is you want to think about the U1, U2 plane. You want to think about the unit square in that plane. And to think about these probabilities, you want to interpret this inequality graphically. Maybe I actually should use capital U's here. It's a little weird, but it might make more sense. U1 plus U2 being less than or equal to S, where S is an arbitrary number. Between 0, here's something new, between 0 and 2, not 0 and 1. Right? Because if U1 and U2 are both really, really close to 1, then their sum is really, really close to 2, and I can make it arbitrarily close to 2 by making U1 and U2 sufficiently close to 1. The equation capital U1 plus capital U2 equals S can be rewritten as capital U2 equals S minus capital U1. And for a fixed value of S, graphically in this picture, its graph would be a straight line with a slope of -1 and a vertical intercept of S. In other words, if S is, say, right there, the graph of this equation looks like this. A line with a slope of -1 and a vertical intercept of S. When S is in the case where S is between 0 and 1. In the case where S is between 1 and 2, it's the same equation, but now the graph looks like this, and I'm only going to boldface the one that's in the rectangle, the square here. That's what the graph of this equation looks like when S is between 1 and 2. And this probability is the probability that the sum is less than or equal to S, not equal to S. Graphically, that corresponds to the volume under the joint density above a given region, like above this triangle, for example, when S is between 0 and 1. But again, because the height of this graph is 1, the volume under the graph is the same as the area of the region, the area of the triangle in this case. This area is the value of capital F sub S of little s when S is between 0 and 1. Little s is between 0 and 1. And it's a triangle, so its area is base times 1/2 base times height is 1/2 s squared. When s is between 1 and 2, then we think about the area that's still in this square that's under this other graph. But I got to stay in the square still. So it's the area of not a triangle anymore. A region like this that I could break up into a rectangle, another rectangle, and a triangle, but it's probably easiest to think of it as the area of the entire square minus, or subtracted from 1. Yeah, 1 minus, I meant to say 1 minus the area of this triangle. Up here. Calculate this as 1 minus that area. It's a little tricky. You got to figure out what the coordinates of these points are. When u1 is 1, what's u2? Plug into that formula, you get s minus 1. The coordinates of this point are 1 comma s minus 1, that point right there. And the coordinates of this point by symmetry are s minus 1 comma 1. And this distance then, right here, is the second coordinate of this point is 1. 1 minus the second coordinate of that point, which simplifies to 2 minus s. Yep, that's right. In the case where s is between 1 and 2, that distance is 2 minus s. I mean, think about it. When s is 1, and the line looks like this, 2 minus 1 is going to be 1, and the length is 1. When s goes up to 2, the line's going to look like this. 2 minus 2 is 0. The distance is going to be 0. That's confusing. Just think about it carefully after class. So what I'm trying to say here is this ultimately is also an area that's shaded purple. And that area is 1 minus the area of that triangle. And the area of that triangle is that. Simplify. And you're left with negative 1/2 s squared plus 2s minus 1 if I've not made a mistake. And this, if you factor out a negative 1/2, I believe might be factorable, maybe. Maybe not so nice today. Did I do that right? I was thinking that might be a perfect square, but it's not. I don't know if I maybe made a mistake here. Anybody see any mistakes? Or my mistake could be up here, actually. Looks all right. I don't see a mistake. Right up there? Is that what you mean? Yeah. I'm subtracting the second coordinates. The second coordinate to this point is 1. The second coordinate to this point is s minus 1. 1 minus s minus 1 simplifies to 2 minus s. S is between 1 and 2, so this is a number between 0 and 1. I don't see any mistakes. If I graph this CDF, this proposed CDF, it's a piecewise function ultimately. Do the pieces match up at s equals 1? Between 0 and 1, the formula is 1/2 s squared, whose graph will look like this. and have a value of 1/2 when S is 1. Does this have a value of 1/2 when S is 1? It does, actually. Plug in 1 there. You get negative 1/2 plus 2 minus 1. 2 minus 1 is 1. 1 minus 1/2 is 1/2. And its graph is an upside down parabola, negative coefficient there. Is its value at 2 equal to 1? Let's check that. Negative, plug in S equals 2. 2 squared is 4 times negative 1/2 is negative 2. Plus 4 is positive 2 minus 1 is 1. Yeah, it is correct. It's a continuous function. It looks like this. And the PDF would be a piecewise function as well. Differentiate this piecewise, you're going to get, in the first case, the derivative of 1/2 S squared is going to be S. And the derivative of this thing is going to be ultimately negative S plus 2. And the graph of the PDF, if you graph this piecewise function, is a triangle. That's the graph of the PDF. Hey, how do I really relate this to chapter 6? This is my last comment. I added these two random variables there. If I just divided them by 2, that would be taking their mean. I could call it X bar, sample mean. I didn't divide by 2. I could have. This is almost the distribution of the sample mean when the sample size is 2. If I divided by 2 up there, what would happen is this would change for F to be S between 0 and 1. Because if I divide a number between 0 and 2 by 2, the result is between 0 and 1. The graph would look the same, except this would be a half, this would be 1. The height would be different. But it still would be a triangular distribution, which is closer to looking like a normal distribution than a uniform one is. I won't finish it in class because we're out of time, but you could simulate this. You could go back to the spreadsheet. Make one more column for the sum of U1 and U2 equals D1 plus E1. Oops, forgot my plus sign. Equals D1 plus E1. And sometimes you get numbers bigger than 1 here. In fact, about half the time you do. And the mean should be close to 1. It's symmetric. It's a triangular distribution, which is closer to a normal, which is hinting at the central limit theorem as n gets larger and larger. All right, have a good day.